Okay, thanks. Okay, welcome everyone. Tom Steph will be moderating, but I just want to open up and talk about a couple things before we get started. If you haven't attended before, a lot of you I know attend monthly, so you've heard this before, but just in case, if you're having any audio issues, need any kind of webinar support throughout the presentations, right here on the home screen, you'll see there's a phone number to contact to get help there. And also you do have a chat box and a questions box so you can ask questions at any time if you're having issues. And just in the handout in your navigation bar, you should see a handout drop down. We did include the slides there, so if you want to follow along on your own slides, you can do that. Today, like every webinar we do each month, we do offer a continuing education contact hour. In order to get the certificate, you do need to attend the live webinar. Although we do post recordings of these webinars within a couple weeks, we can't offer certificates for watching those. So either if you're logged in or you're in the room with someone who is logged in, the person in the room with you can provide us the names of everyone in the room via this email here you see in number 3 to Cadmus, and we will get you those certificates within the week of the webinar. And if you registered and you forgot to check yes for the certificate, it's the same thing. Go ahead and send us an email and we will get that certificate sent out to you, as long as you attend for a full 60 minutes. And with that, I think I'll turn it over to Tom.
Okay, great. Well, today's the first in our webinar series. In the past, we've always had a EPA speaker. This is the first time we've had 2 people from outside the agency present. And so we have a disclaimer that we need to read through. So here we go. Any mention of trade names, manufacturers, or products does not imply an endorsement by the U.S. government or the U.S. Environmental Protection Agency. EPA is distributing this information solely as a public service. Both LB Water, Flow Networks, and Virginia Tech are responsible for the quality of this information. EPA's distribution of this information does not represent or imply endorsement by EPA. EPA and its employees do not endorse any commercial products, services, or enterprises. So with that, thank you for listening in. I will introduce our first speaker, John Brutz. John is the General Manager of Flow Networks. His core work involves helping communities establish and implement leak detection and inflow and infiltration programs with modern technology integration. In 1988, John began his career in the waterworks industry, where he operated and managed water and wastewater treatment plants and distribution and collection systems for over 19 years. John attended the Indiana University of Pennsylvania. And with that, I'll hand it off to John for his presentation.
Good afternoon, everyone. So today I'm going to talk to you guys about water loss management, ways to reduce non-revenue water, NRW. Hopefully I'll show you guys some new ways, new concepts, and things you might not have previously been exposed to. And to get started, Benjamin Franklin probably, although he wasn't involved in NRW, he probably said it better and realized this well before we did. When the well is dry, you truly learn the worth of water. And I think everybody on this phone call probably has been in tune with and in touch with just how big of an issue this really is. I put a couple, cruised the internet, found a lot of good articles. The North American Water Loss Conference, that's coming up again in 2017. Everybody heard about the droughts in California, states running out of water, the efficiency, the cost, and all of this. So it's definitely become a very large, very high profile nationwide issue. Some really good information on here. If you look at some population statistics along with water withdrawals, you can see in 1950, the population in the U.S. right around 150 million people, and in a short 60-year period, we've doubled that. And if you look at the projected water withdrawal, actual withdrawals and projected, that pretty much mirrors As population grows, so does the need for water, for available fresh drinking water. What's really troubling to me is I've been in the industry, as you guys heard, since 1988. I've been at this for quite a while. And you can see I did a policy survey in 2002 that was taken at that point in time. That was probably the best information available. You can see where the states nationwide, what we had available for unaccounted for water at the time. We didn't even talk about non-revenue water. We talked about unaccounted for. We used the basic percentage method. Most recently, Will Jernigan, who's with the AWWA National Water Loss Committee, him along with George Kunkel have been really doing a lot with the water auditing, that type of thing. And you can still see, however, when you look at this chart, this graph, if you will, the light blue represents no water loss reporting standards whatsoever. So quite a few states are doing nothing regarding water loss. The ones in pink or salmon colored, very rudimentary water loss standards. A few are starting to use very basic AWWA M36 metrics. Two, or actually three now, are using software, and only three, Georgia, California, and Hawaii, are doing full-blown water audits. So again, if you kind of couple those things together, it's a little bit troubling. We've got population on the rise, water usage on the rise, and really no regulation to help us more effectively manage this. So I put a slide in here. Everybody that's involved with water treatment and distribution, we know more so than the general public there's a real cost, a real value assigned to treating and distributing, pumping water. In the northeastern PA, where I've been doing a lot of research, northeastern part of the country, I've seen people that have their own treatment sources, whether it be a well or filtration plant, a dollar value, a real cost of anywhere from $1 to $4 per thousand for treatment and distribution. Obviously, if you're a pretty good groundwater source with very basic disinfection, you're going to be on the lower end of that. If you're into full-blown filtration, that type of thing, you're going to be on that higher end. And also, we also see out here, too, a lot of the people that are consecutive systems that are purchasing from another supplier. I've seen those costs as high as $5.50 to almost $6 per thousand. So again, when you start, you look at these numbers, it's pretty eye-opening. And I put together in Pennsylvania, the Pennsylvania DEP has had on the books since, well, I got into business in 1988, the very basic 20% water loss number. And that represented, it was recommended that you stay below that. That comes into effect if you're looking for a renewal of a water allocation permit, that type of thing. Annual water supply reports that's reported on there, that 20% is the magic number in Pennsylvania code at the moment. Well, when you start, and that's the reason I picked that 20% was the recommended number. Well, when you start looking at the chart, the treatment distribution costs, that $1 to $4 per thousand. So let's say that you're a guy that has a $3 per thousand treatment cost. If you look on the chart on the left, then you're losing 20% of your water at a basic unaccounted for water percentage number. And let's say you're 500,000 gallons a day. Essentially, you're losing 300 gallons per day, or $300 per day. That's costing you $109,500 per year in real loss, real cash that is basically being drained into the ground. And obviously, if you start looking down the chart, the larger you get, the higher your production cost, the bigger that number becomes. So if you're a 5 MGD guy, 20% loss again at a $4 per thousand treatment, you're losing $4,000 a day, or roughly $1.5 million a year. So I think, that's one of the things that people come to work in the morning. I was no different through the years. You make sure your pumps are running, your treatment process is going as it should. And you don't really see those subtle increases in, I have to order an extra barrel of aluminum sulfate this month. I need to, maybe get another 150-pound chlorine cylinder. My electric bill went up a little bit. But when you really start getting into this, probably one of the biggest things I could leave everybody with today, if you're not looking at that relationship between what you're treating and pumping versus what you're losing. That's definitely the first starting point for sure. And as I like to throw in here, Einstein said it better than I ever will, the true definition of insanity, doing the same thing over and over again and expecting different results. So honestly, if you expect that you're going to go to work tomorrow and your flows are going to be down this, that, or the other, I really don't think that's going to change. And as I said, it's imperative that you really take a look at those numbers, see where you're at, see what your losses are, what your potential gains could be. And with all that being said, so now that I've painted the picture of doom and gloom, how do we eliminate the loss? So essentially, a very tried and proven method, a four-step approach, if you will. Identify the water loss through a water audit, implementation of DMAs / submetering, implementation of a good leak detection program, and pressure management. And the pressure management, some systems I realize you don't have the altitude changes of the nature of the geography of where you might live, so I'll cover over that one a little more rapidly. So the water audit, as I said, if you guys aren't familiar with this, AWWA does provide this for free. There's a very comprehensive free software. The 4th edition of the M36, basically a top-to-bottom spreadsheet where you're looking at all of your sources, whether it's imported, your own source, looking at the total water supply, what you're exporting, and you're breaking it down from top to bottom to see where all that water's going. The topic of my presentation today, I'm going to focus more on the real loss. However, you cannot overlook your meter inaccuracies, old meters, aging meters, that type of thing. And the one thing I really would call your attention to today as well is you really need to pay attention to all of your input, your source meters. If you're basing all this information off of a 1980 Rockwell turbo meter that hasn't been calibrated or accuracy tested, again, your results might be staggeringly off. So again, but that is all outlined in the software top to bottom approach. And again, it's free. One thing to keep in mind when you start considering real losses, excuse me, got a frog in my throat. Technically, real losses are broken into 3 categories, where you have background leakage, unreported leakage, and reported leakage. So basically, what this is showing you, the reported leakage is how fast you respond to a leak that has surfaced. Someone is called in from the time you're aware of it till you shut it down, stop the bleeding, and make the repair. The unreported leakage is leakage that's occurring underground but not surfacing, that can be found with acoustic methods, acoustic equipment, things of those nature, things along those lines of that nature. The background leakage. So this is seepage, leakage, plastic splits that are there when the pressure is up, disappear when the pressure decreases. These typically can't be found by any type of standard equipment. This is where we get into the pressure management. And a good way to think about that would be if you were to take a 2-liter bottle and cut a little slit in it, hold that bottle up. We all know the water is going to seep out. Increase pressure, squeeze the bottle, and you can see how much more water comes out. So that's what we mean when we start talking about pressure reduction, background leakage, and that type of thing, and how we address it. So the first category we start looking at is DMAs or submetering. Simply a way to break your system down into districts, as you see here. So rather than looking at water losses across the total system, we can now start to break it down in smaller, more manageable pieces, more manageable segments. The concept was a great idea. However, historically, there were a lot of barriers. Number one, the price. Typically, the lines that you want to submeter, very expensive to do. You pray that the valves hold whenever you go to shut it down and cut in a monster pit like that, so it never really caught on. Fortunately, today, we are capable of doing submetering with an insertion probe, as you see here, a true electromagnetic meter that we can achieve low flows, measure the velocities, and determine where we have leakage when we create the DMAs. And all of this data can be locally downloaded, tied into your metering systems, your AMI, your AMR reading systems, as well as standalone GPRS cellular technology. So all that data can be pushed to the cloud through your metering system, whatever the case may be. The next couple slides will probably best define this for you. This is an example of a customer I worked with that did have a mag meter, an inline mag meter at a treatment plant. And we did an insertion meter to show them the difference between monitoring minute by minute versus on a daily basis. So these guys, I downloaded the data and showed them what they had been doing was sending a guy out for this particular treatment plant every day at noon, subtracting yesterday's reading from today's, looking at the total volume, and then dividing that by 1,440 minutes in a day. And as you can see, over the course of that 1 to 2 week period, they were flowing at a rate of roughly on average 400 gallons per minute. And the question I asked was, all right, so you're flowing 400 gallons a minute, how much of that is leakage? And of course, they couldn't provide an answer. And then this is when I showed them looking at that same data set on a 1 minute basis as opposed to that 24-hour snapshot. We can see that our minimum night flows were right around 200 gallons a minute. So they didn't have any large users, any large consumers downstream of this meter. So they did, in fact, have roughly a 200 gallon a minute loss. What the guys did is they did go out and they surveyed their system. They found 3 leaks. They made the repairs, and you can see right around November 25th, their minimum night flow did zero out. They were pretty ecstatic about that. However, the bad news or the good news, however you want to look at it, we were able to see that leakage did occur again. Another break started roughly on November 3rd at right around 25 to 30 gallon a minute. And you can see the rate of growth due to leakage by monitoring those minimum night flows. So again, when you start looking at overall water loss, response time, water consumption, you can see how breaking down your system into manageable components, the value you can obtain out of that. So that leads us into the next point. So we know downstream in a particular DMA, we do have leakage. Well, how do we find it? And I like to use the analogy, if you're going to eat an elephant, you eat it one bite at a time rather than trying to shove the whole thing in your mouth. Not that I'm advocating eating elephants in any way, shape, or form, just to clarify that. But anyhow, essentially that's what you're doing. So you take a gridded part of your system. In this example, we know that this DMA contains the leak. How do we find it? So essentially, technology has brought us to the point, again, we're looking or listening for acoustic energy, listening for sound, if you will. The technology has brought us to the point that no leak detection experience is required like it used to be, where you had to have a trained ear. Essentially, anybody that can drop a valve or an acoustic sensor on a valve nut, like the guy on the right, is capable of being a top-notch leak detector. So how this translates is if we were to sweep this DMA with acoustic loggers, the loggers are going to do the listening for us, and programming can be varied. However, the most common time is in the middle of the night. In this example, you can see on the right, we have our red indicators that there is a leak. It's kind of hard to see on there, but these loggers, in addition to showing us, yes, there is a leak, they're showing us the amplitude, the decibel level, how loud it is. We can start to create relationships based off of sound travel from one logger to the next. So essentially, just by looking at an acoustic logging profile, we're able to see that, yes, the leak is on this block between these 2 loggers closest to this logger. So we're able to very rapidly narrow this to street level. All of the product manufacturers out there have different variations, different ways of doing it. I have some screenshots on here. So when you do retrieve the data from the loggers, the bottom right, you can see where some permanent logging was occurring. We can see as the leak started to grow when it was officially identified as a leak. In addition to seeing the amplitude, the decibel level of the leak, the lower left, we can also record sound files and see the frequency of the leak. So in some situations, if the culprit may be one leak, seen several where we saw 3 separate frequency indicators or indicating 3 separate leaks at 3 different frequencies. So very powerful information. And with the web-based, cloud-based applications. We can do Google Earth Street View, zoom in. If we were standing right there, we can look at possible sources of noises. Maybe it's a pump station, maybe it's a transformer, things of that nature. Once we know that the leak is on the street, what street it's on, where do we dig, that's when we get into correlation. And correlation, we can use traditional methods, or we have the ability now to remotely correlate via satellite. There are technologies available that the loggers log amplitude. If leak noise is identified, that information along with a true audio file and frequency analysis is pushed to the web. And essentially we can pull that information from our couch with a tablet, a laptop, do multiple point correlations as you see, and pinpoint the source of that noise. So again, a lot of methods, technologies available to help with this problem, which leads me into the last segment of my presentation, which is pressure management. And as you can see, I just have a snapshot with pressure reducing valves. Typically, as we all know, pressure is a function of elevation. Most states are regulated with maximum pressures we're allowed to provide to customers. Typically, once you exceed 150 psi, you're required to do pressure management or pressure regulation, I should say. And the way a PRV works is simply high pressure water typically goes on top of a diaphragm. If no water is desired downstream, the high pressure water pushes down and closes the valve. As demand occurs, the water is exhausted off of the cover, the top of the diaphragm. The valve is allowed to open and supply water downstream, and that's all done through a pilot valve, as you see on the right. Historically, fixed outlet was the common and still is the most common method of pressure control. Essentially, we picked, as you saw in my first slide on this, we have a desired or an incoming pressure of, let's say, 120, and we want to maintain 50 psi downstream. We simply adjust the pilot to supply 50 psi. Over time, somebody got pretty smart though and said, hey, you know what, why are we supplying all this pressure in the middle of the night whenever everybody's sleeping and we don't need that pressure? So what they started to do and what started to pop up were solenoid control timers on the PRVs, where essentially between the low flow hours, 1 a.m., 4 a.m., 5 a.m., maybe instead of that 50 psi, they would knock that pressure down to 40, maybe 35, take that pressure off. Back to the analogy I mentioned earlier where you squeeze the 2-liter soda bottle. So the less pressure you put on that leak, the less flow, the less loss. Well, then somebody got even smarter and said, hey, why are we doing that? Why don't we just modulate pressure and supply pressure when it's needed? If no pressure, no demand, let's lower the pressure. If pressure is needed, let's open that valve and supply what's needed. So if you look at a standard fixed outlet PRV situation and we were to pressure log this, you would notice that the PRV, the 50 psi scenario that we mentioned, that PRV is always going to hunt for and try to deliver 50 psi on the outlet side of the valve. All the while, if you were to monitor the critical point, which would be the highest elevated point downstream in that pressure district, you're typically going to see as the valve tries to maintain that pressure, high flow, high demand periods, you see a pressure drop. In the middle of the night, you see that pressure increase. Very repeatable. The whole concept of pressure management is flip-flopping it. So we decide what critical point pressure we want to maintain. We pressure log that. We send the information to the cloud. In this example, let's pretend that that's 30 psi at the critical point. We modulate the valve to always supply and maintain 30 psi to that critical point. When we do that, this is a real example of an unmodulated valve. So you can see in the red, the black, the PRV inlet pressure we didn't have control over. We pressure logged the PRV outlet pressure in that fixed outlet situation. And you can see as predicted, the critical point pressure in the lime green. Off-peak hours, pressure spikes when there was demand. Even though the valve's trying to keep up, we still see the pressure drop. And if you notice the flow, the flow and pressure obviously are interrelated, we looked at and monitored the minimum night flows. So you can see where our night flows are. You can see right whenever we flip to pressure control, and basically we started getting pretty close to a steady, stable critical point pressure, and the resulting outcome was in this little example, a 30 gallon per minute minimum night flow reduction, 66% saving on that DMA, simply by modulating that PRV, supplying the pressure when it was needed, taking the pressure away when it wasn't. And as you can see on here, that's definitely a very dramatic and instant leakage saving, no doubt about it. You also gain a nice stabilization of your network pressure, and as you can see, stable pressure means a lot less bursts or breaks, recurrence of leakage, the need to detect and repair leaks, and everything else you see on there. So definitely a big value in pressure reduction. And again, not, when you start looking at that, it's a case-by-case basis. Not all systems will have that opportunity, nor will all pressure districts be candidates. So if you have a PRV feeding a pressure storage tank, the PRV shuts down, and now you're supplying back pressure from the tank. Obviously, that's not going to work. So again, those are analyzed on a case-by-case basis. And in summary, I like to use the old quotable quotes, and like my dad used to always tell me, waste not, want not. I never really understood what that meant until we got to this point in time, especially when you start talking about water management. So much holds true. And on that note, I think I'm pretty good on time, and that was everything I had in my presentation today.
Okay, thank you very much, John. And
you're welcome.
So we have, thank you very much, and we're all set to go. A little housekeeping in between talks. First of all, if you missed the poll question at the beginning of the webinar and have more than one person in your room, please type that number into the question box on the dialogue portion of your screen. This will help us document how many people are attending the webinar and helps us justify it. Also, if you're right, and for certificate purposes also. So that would be very helpful. Also, if you have any questions, I forgot to mention it at the beginning of the first talk. If you have any questions for our speakers, the first or second talk, please put them in the question box, and we'll answer them at the end of the second speaker, as we typically do. And we'll try to finish up by the top of the hour, and then we'll spend some time after that answering whatever questions still remain. Finally, we have the small systems workshop here in Cincinnati, August 22nd to the 24th. And I just wanted to put in a plug for that. And there will be a link in the chat box that you can see that links to the webpage explaining more about the small systems workshop, where we bring in state primacy agency people and work with them on what research would be helpful to them in answering their questions they have, and also disseminating some of our the research in the field from EPA and others. So with that, I will then introduce our second speaker. I've been told I don't have to read the disclaimer a second time, which is really good. And so I'll go right into introducing our second speaker, which is John Matthews. John is an associate professor of civil engineering and construction engineering technology at Louisiana Tech University, and is the director of the Trenchless Technology Center. For more than 10 years, his research has focused on innovative technologies for the assessment and rehabilitation of water and sewer pipelines, and that has resulted in more than 140 technical publications. John is an active member of the North American Society for Trenchless Technology, where he serves on the board of directors. John holds a BS in construction engineering technology and an MS and PhD in civil engineering from Louisiana Tech. And with that, I will hand off the podium to John Matthews. Hey, John, we can't hear you.
Hear me okay, Ty?
Oh, now we can, yes.
Okay, good. And my screen's okay? You can see it?
Yes, we can.
All right, thanks. All right, first I want to thank Tom and thank the EPA for inviting me to speak. Appreciate the opportunity. And I like the setup of this webinar. My presentation, which focused on rehabilitation, is a good transition from John's, which was focused primarily on leak management. So we're going to look at sort of that next phase and talk about repair and what some of the options are there. Also wanted to highlight that there's a lot of information out there on rehab and pipeline repair, and so we're really limited in how much we can cover here. So throughout the presentation, I'll be mentioning a few references of additional information that you can go to, and of course feel free to follow up either with the organizers or myself if you need help tracking down additional information on some of these resources, because as I mentioned, there's quite a wealth of information out there. So I'll be focused on rehab technologies, and let me see if I can advance here. Yes, there we go. So an overview, just a little bit of a background on water main rehab, what that means, why we do it, some things like that. And then I'm going to actually go over, similar to the way John did it, go over some specific technologies. I'll try to explain it as detailed as possible, realizing that probably not everybody has a background in all the different maybe mechanisms that we'll be talking about it, but I think this will be detailed enough for you to sort of get the gist. And if you need additional information, you can go back in and find it. And then I'll just do one little slide on sort of what are some of the factors on how you would select maybe between one technology and another, and maybe just give some brief examples, but not go too detailed on that. So just some background first on water main rehab. Pipelines are reaching the end of their useful life for various reasons, not just for age. There's different operational considerations, environmental considerations to where a pipe would deteriorate and eventually fail. Obviously, pipelines, we don't want them to fail, but sometimes it happens. Sometimes it can be catastrophic, as you see from the pictures I have here to the right. Unfortunately, these aren't odd cases. These happen quite a bit across the country every day. And so, you know, what can we do to help maybe prevent that, maybe get a little bit better handle on that? There's some things we can do, but it's tough. You know, we're limited with the budgets that we have. Many utilities are very much in a reactive mode. Not all, but some. That's, you know, the best they can do. But when you're reactive, you're doing emergency repairs and things like that, your costs are typically higher, and you also don't have time to really prioritize and budget for maybe long-term planning of asset replacement and rehabilitation. So ideally, we'd like to be able to get in front of these things. Some are able to do it better, but it's a process, and this is essentially what I spend most of my time doing is speaking to people from both the municipal sector to try to help them do that, and then working with technology developers to help them address the needs that utilities have, and also work with engineers to make sure that they have the information they need to spec the right types of technologies. So when you look at not having enough money or enough budget and things like that, that really makes us feel like we need to be more proactive and maybe go towards the function of using things like asset management principles. And so a lot of what you'll see now when it comes to pipeline management is related to asset management. And a big some keys in asset management have to do with sort of what you have in terms of inventory, what condition that it is in terms of inspection, and then what you do with it in terms of action. So we're really talking about the action portion today. You know, how can we address pipelines that we either know are definitely bad, or through some type of desktop assessment or condition assessment, we suspect they could fail relatively soon. So how do we address those going forward? And so the first reference I wanted to mention that I put at the very bottom of this slide, I apologize, it looks like the text is sort of fading there, is AWWA, the American Water Works Association. They have many manuals of practice. One of those is M36, which is focused on pipeline rehabilitation. So it's something to jot down as a potential useful resource as you look into doing this type of programs and pipeline replacement. And why rehab versus replacement? In some cases, rehabilitation can be more cost effective if done correctly, and many times can extend the useful life of that asset very long. And so if you're getting the cost benefit and the payback and the long-term payback is there, in many cases rehabilitation can be a best solution. Understanding that we're talking here primarily about distribution system water mains, I should just highlight that rehabilitation, as we're going to be talking about today, which focus primarily on trenchless technologies, which are less disruptive technologies, so not just digging the pipe up. Those are relatively, I would say, young compared to rehabilitation technologies for sewer systems, which have been used for many more years, upwards of 40 and almost 50 years in some cases. Most of the technologies we're going to talk about here today are more in the 10 to 20 year range, so not as long of a track record, yet still some proven successes, and definitely have a place in a utility owner's toolbox when it comes time to manage their pipeline assets. So I hope that's a good general background. I do want to highlight some research that the EPA took a leadership role in, sort of serving as that institute or that agency to be able to help utilities, sort of like these webinars are a part of, to gain access to this type of information. A few years ago, the EPA had a aging water infrastructure program. I forget the exact years. I think it was 2008 to 2015, something like that, maybe longer. And over the course of that program, I produced lots of valuable information and research and data on different technologies for essentially managing pipelines. And a big part of that had to do with rehabilitation. And so a couple of the key reports, again, this would be some resources that you should jot down. These are publicly available on the EPA's website. But one of those key reports was a state of technology report on water main rehab. So a lot of the technologies I'm going to talk about here, where I have one slide on, may have a whole chapter or a few pages in those reports, or in that report. So keep that in mind as a reference for your future use. Another key part of that program was looking at demonstrating under actual field conditions with actual utilities some of the more innovative techniques. So some of the things that were at the time probably less than 10 years old, 5 to 10 years old, and making sure that those would be useful for utilities in the end. So they, the EPA and their contractors ran them through a series of tests in the field and the lab to make sure they're applicable. And there's a few reports out there on that. There was also some projects that were co-funded through the Water Research Foundation related to that topic. And those reports are also publicly available through the Water Research Foundation website. So keep that in mind, make a note of that for some additional information. As the sort of a transition back to John's presentation, there was also quite a bit of work done looking at innovative condition assessment technologies, and that included leak detection. And so there's multiple reports out there on that where they did the same thing, state of technology reports, and also some innovative technology demonstrations. So mark that down as well for some additional information. So lots of information out there. I'll do my best to try to summarize what some of these key technologies may be, give you a little bit of background, and talk about where they're applicable, what some of the advantages and limitations are. Hopefully enough to at least get the interest up to where you can pursue additional information if you need it. So first technology I wanted to talk about is called pipe bursting, or pipe beating, which is a modified version, and essentially involves breaking up a pipe that's in the ground. I realize on that picture you can't actually see that there's a pipe in the ground, but where you see that steel tube going into the dirt, that's actually already inside of a pipe that's in the ground. It was deteriorating, and so this method, you pull in an expansion head basically that breaks up the old pipe and leaves it in the ground and pulls a new pipe. You can barely see on the left there, that's a new plastic pipe being pulled in behind, all at the same time. And so As I mentioned a little bit early on, we call these trenchless technologies, so we try to limit how much we dig, and so you would have an access pit at one end where you would pull this into the pipe, and then you would have an access in at the other end, maybe 300, 500, 600 feet down, where you would pull the head out as it's being pulled down. And so it's limited trenching, you know, minimize disruption. That's really the basis of what we call trenchless technologies and everything we're going to talk about. So pipe bursting has been around a long time, actually. It was developed in the 70s or 80s, I think in the 80s, by in the UK for gas main replacement, actually. And so it's regularly used in the US for both sewer and water. Smaller diameter pipe, not really for the larger pipe. Maximum may be up to like a 36-inch pipe, but we regularly see it on 6, 8, 10, the kind of sizes we would regularly see in a distribution system. One of the key advantages, I realize one of my headings is wrong here, that should actually say pipe bursting. One of the key advantages here is you can actually upsize with the pipe diameter. So if you have an existing 8-inch and you need more capacity, pipe bursting is really the only tool besides just digging the pipe up where you could pull in a 10 or a 12-inch. And as you break that 8-inch pipe up and it compresses into the soil, you could pull a larger pipe in. So that's a big key advantage for it. And also it can typically withstand any load. That plastic pipe that was being pulled in on that picture you saw before, that's the fully structural standalone pipe, just like you would bury, direct bury. So that's a big benefit to get essentially full service life, just like you were doing a trench and putting a new pipe in the ground. You see that classification. I'll reference to classifications regularly for the structural classification. That is in reference to that AWWA manual that I mentioned earlier. It's 1 to 6 with class 1 to class 4, with class 4 being the fully structural and the strongest one. Some of the limitations, again, on bursting, that shouldn't say sliplining, is you do have to excavate for service connections. So if you have a lot of service connections coming off of your distribution pipe, which is sometimes common depending on the nature of your neighborhood or the way the pipeline's laid out, that's something that needs to be taken into consideration. They do relatively small excavations there to reattach the service, but it's an excavation nonetheless. So something to be taken into account. I would say one of the key limitations, you know, especially if you have lots of service connections. The next technology would be sliplining. The service connection issue applies here as well. Sliplining is essentially, instead of breaking that hose pipe up, you're leaving it in there and you're just pulling a smaller pipe inside. So obviously you're not able to upsize or make the pipe bigger, you're actually making it smaller. But with the close fit liners, where they actually roll it down temporarily before it's re-expanded, you get really close contact with that hose pipe, so you don't lose a lot of capacity. And actually in cases where you have to do some extensive cleaning, sometimes you even improve the flow characteristics of that pipe. So something to be taken into account. Sliplining has been around a long time for lots of different applications, and it is used on water mains in some situations. If capacity is a big issue with a pipeline, you probably wouldn't use it because you are going to lose some capacity. But if you're able to lose a little bit based on your hydraulic modeling and things like that, this could be a potential use for you. Specifically for long segments, it's really good. They'll fuse together long sections of plastic pipe to pull into the hose pipe. And if it's relatively straight, it works great. One of the limitations is when you start to have bends. It can address bends, but anything too large, that they like to set excavations at those directions and keep pulling a new liner. So you can get a class 4 liner with this as well, fully structural, but you also see semi-structural class 2, class 3, which obviously don't have the same service lives. But class 4 would have a full service life, just like a new pipe. Some of the limitations, the reinstatement issue still applies, similar to bursting, so you may have to put additional pits if there are services. Yes, the largest reduction in diameter, as I already mentioned, comparable to some of the other technologies we're going to talk about, and then some conditions with the bends, as I mentioned. The next technology, cured in place pipe, regularly called CIPP, is by far the most commonly used rehab technology for sewers. Been around since early 70s. Probably the last 20 years has been developed for water mains and seen a lot more activity over the last 10 years. So it's a great technology. It's very strong. The difference between the one used for sewers and the one used for water main is that it has to be able to handle the internal pressure. So there's some additional loading capacity to be able to have that hoop strength. And so this is a pilot here on I think that was a 16-inch pipeline out in Las Vegas. So it's a commonly used technology in rehab in general, and it's used quite a bit on water mains now. Again, they're very strong. They have various different layers of reinforcement in them, either from carbon fiber or glass fiber. And the liner itself, those not familiar with CIPP, is actually starts off as just a sort of a soft foam or felt, and then it's impregnated or wetted with a resin that, when heated, it cures and hardens to basically be like a pipe within a pipe. And so you add layers of reinforcement to add additional stiffness and strengths to it. And so you can meet a class 4 fully structural. One of the benefits over the first two technologies we talked about is you can actually reinstate service connections internally, robotically, without having to excavate. So that, not always, but many times you can. So that's a big benefit. It's able to align through various types of bend conditions, so that's a benefit. You can't really line through valves and other appurtenances though, so anytime you have those types of things, those are used as access pits. The links are relatively, I would say, a little bit shorter than you would see on sliplining. They're probably closer to what you see on bursting though, so it's not really a limitation, just something to keep in mind. If you had a long stretch of a couple thousand feet that you knew you wanted to line, if you're using CIPP, you might have to have a few access pits in the middle to meet that full couple thousand feet, whereas maybe sliplining, maybe if it's straight, you might could go the whole way or something like that, maybe only one pit. So just a few things to think about. When it cures, it's right up against the pipe wall, so it's really tight fit. The liners are relatively thin and strong, so you're not losing a lot of capacity there, so that's a good thing. It has to be pretty clean though. I'd say one of the limitations, you have relatively high cleaning requirements. It doesn't have to adhere necessarily, but it does have to have a tight, clean fit. So you have to get all of your debris out and things like that. So a couple more technologies I want to talk about, and I'm not sure, I almost left this out, I'm not sure how much it's applicable to smaller systems, because this is really designed for larger transmission mains. So everybody has, you know, what we call transmission mains or feeder mains, but these are for really large, you know, person access mains, where they go in and almost do like a wallpaper type thing, but it's called carbon fiber reinforced polymer, CFRP wraps. It's basically layers of reinforcement and resin that are hand applied, and they're very strong. They're used in structural applications all the time, civil engineering structural applications, and now is used in pipelines, NSF 61 certified, so internally or externally. But really limited on your diameters there. So for smaller distribution type sizes, not really applicable unless you're doing an external wrap. But if you're doing an external wrap, you probably had to excavate, so not as much benefit there. But if you do have a pipe that's large enough, and maybe you only needed a few spots repaired and not the entire length or a very long length, this is a very good technology, very strong. Another class 4. You can fit it around service connections if you have any, even though we don't really see those in transmission sizes. So not really applicable necessarily, but if you did have service connections, you just kind of fit it around them, so that's a good thing. And of course, if you're person entry, you can kind of go around bends and all types of things, so not really limited there, but you're limited by the diameter, so it's kind of a catch-22 anyway. You won't lose much capacity. These are very thin, strong carbon fiber layers that are just put on with different types of resins and cured. So you're not really going to lose any capacity of any substance. I'd say limitations besides the person entry and the spot repair would be the cleaning requirements. You know, this does have to actually bond, just like if you were wallpapering a house. I shouldn't call it wallpaper, but just to kind of give you the gist. You need a really clean surface that you can bond to. So another spot repair would be like a joint seal. So if you go through or you find out that you have these leaks like John talked about, and maybe they typically seem to be located at joints, there are a few sealers that you can put in just at the joints to address that issue. With various types of gasket, that picture there is a rubber gasket with a metal ring. There's different types. One of the limitations would be these are really only applicable for person entry, though. There are a few that have been developed on the sewer side for non-person entry, but to my knowledge, those aren't really used that much on drinking water. So maybe something in the future. But so some advantages of these seals: they mechanically lock into place. They can seal joints and pinholes. It doesn't really apply to service connections, so I would say that's actually a benefit. You don't have to worry about that. But again, mostly limited to person entry. It's a non-structural, so this is really the first one we've talked about that's not or couldn't be a class 4. Non-structural would be considered a class 1. This is just for sort of that leakage barrier. It doesn't really carry any structural loads necessarily. And it's not really applicable around bends, although there's one on the sewer side that was developed to go through offsets, so the pipe has a little bit of offset that may, if it comes and gets certified for water mains, it may get to the point where you could use it, but it's not really applicable now. And the last one, I think this is the last one I want to talk about, is different types of spray-on coating. So like spray-on cement and mortar is one of the oldest water main rehab technologies, and actually most new ductile pipes that we put in the ground have cement mortar liners already, and actually other types of pipe too. But you can also do spray-on coatings after the fact, after you've had a pipe in service for many years, for various different reasons, and for various different materials, from epoxies to different polymers and cement mortar. It's quite advantageous for some things. You don't really worry about your services needing reinstatement because it doesn't typically block them. With some of those polymers, they actually cure really quickly. And of course, it being a very thin liner helps you maintain your flow capacity and typically improves it because you have to clean the pipe. But some of the issues would be, I see the last one there. It's not really a structural, I would say unproven really for structural so far. There's a few reports of data out there that some of the newer materials may be structural, meaning it's essentially like a pipe within a pipe. If the pipe falls away over the years, the liner would carry the load. For the most part, what we've seen is that's not true as of right now, but the technologies continue to develop every year, and so maybe it'll continue to go in that direction. But not really structural now. It's more of a class 2, class 3 semi-structural. It can carry some of the loads, but not all by itself. And the high cleaning requirements, I would say, for this one as well, because it needs to have a bond with the host pipe. So I think we covered 6 technologies there. Again, a lot of information I kind of threw out there. I didn't go through it all. There's lots more information if you were actually going to evaluate this technology versus that technology. You may need to know. So just to kind of give you an idea what some of those factors may be, the first one being structural requirements. Does your pipe or set of pipes have additional life in it? Is it going to continue to last, or is it right on the verge of failure, or maybe it has a few years left in it? That would determine whether you needed something like a class 4 fully structural, meaning you think it's going to fail in the next 3, 4, 5, 10 years, or maybe a semi-structural where you think it can carry most of the loads, but it just needs some type of additional support, or you don't have a structural problem, you just have a water quality issue or a leak, and maybe a class 1 type liner or joint repair or something like that would be more applicable. Types of service and branch connections, and really the number of them. If you have a lot of service connections, some of these technologies are not that user friendly. But if you don't have that many, most of them, they're great. So something that needs to be taken into account. Flow capacity, we already talked about. Accessibility, accessibility for pressure mains is it's always an issue. When we're using some of these technologies on sewers, we typically have access through the manhole, so it's not that big a deal. Not always, but sometimes it's a big deal, but most of the times it's not. With water mains, we typically just have to excavate and cut out somewhere, and most of these you can't line through valves and things or hydrants, so you have to kind of use those spots as access and then go back in and replace the hydrant or valve. So that's typically what's done in the industry. And then, are there contractors available? Some of these technologies are quite specific and have specific crews that install them, which of course increases cost. So obviously one of the biggest considerations, but just availability. If you were to put something out there for people to bid on, would there be multiple contractors or would you be limited? So something to think about. And then in general, the technical limitations. Some of these are applicable for smaller pipes, some for larger. Some for long lengths, some for shorter lengths, some with bends, without, all those types of things. So just a few factors to keep in mind when you're actually going to select. And so as you're doing that, or if you need to do that, you're looking for more information, I would say one place would be to start with the EPA and their website, where they publish all that information I mentioned early on from the Aging Water Infrastructure Program. There's lots out there. Of course, you can follow up with them directly. You can follow up with us at TTC. We worked on a lot of that research with them, as did many other researchers. Can hopefully help guide you to the right piece of data if needed. And then also the last one would be if you're looking for specific trenchless technology information, NESTT.org has an extensive library of papers, puts on annual conference and multiple regional conferences, and a great resource for information in this field. So feel free to reach out to any of those organizations or contact me directly should you need more information. So that's all I got here.
Okay, great. Thank you very much, John. And thank you for our first speaker, John Brooks, too, and John Matthews for their excellent presentations. And that concludes the presentation portion of this webinar. We realize some people have to leave on the top of the hour, so thank you for those people. Thank you for attending, and hope that you can attend next month's webinar on August 29th on manganese and iron issues and distribution systems. So if you could come back next month, that'd be great.